Here we are given two populations, Xt and Yt. The almost linear system has the Jacobian matrix Jxy. So they gave us the Jacobian matrix. We don't even need to compute that. We don't know the system, the exact system though. The critical points, so they also give us 4 critical points here. So we know the Jacobian matrix, we know the critical points, we know this one is an almost linear system. So we can do linearization at each critical point. Okay, the first question is linearize the system about each critical point. Then we sketch the phase diagram with a few solution curves. And what about the long-term behavior? So for this question, for the first one, you need to linearize at each critical point. You compute Jacobian matrix at each of those critical points to sketch the phase diagram. So the big picture will based on what happened around each of those critical points depend on what happened with the origin of the linearization. There are two special cases though. The first case where you have the repeated repeated real, so lambda 1 equal to lambda 2 real for the Jacobian matrix of the linearization. And the second case you have, this one is special case where we have the pure imaginary plus minus IB. For the first case, you still know about stability. For the second case, you don't know about any, not even stability, you don't know about that. So let's do this. We consider each critical point at 0, 0 first. Jacobian matrix, let me call it J0. So we have this one is the Jacobian matrix at xy. We going let x, y at 0, 0 here. X equal to 0, y equal to 0. You have 2, 0, 0, 2. So this case, we have a diagonal matrix. So we know immediately two eigenvalues. Lambda 1 equal to lambda 2 equal to 2. Lambda equal to multiplicity or algebraic multiplicity. Two. So this is the special case we have repeated real. Lambda 1 equal to lambda 2 equal to 2. So this case, we know, the only thing we know is that for 0, 0 of the linearization and 0, 0 here is also can also talk about the non-linear system, and 0, 0 of the almost linear system. It is unstable. The reason is that lambda is positive, so it is unstable. However, we do not know about whether 0, 0 of the almost linear system is a node or a spiral point. So one method you can think of that to remember that is this. This case we have repeated real, lambda 1 equal to lambda 2 equal to 2. If a small perturbation happens, this point can split into two distinct eigenvalues. So it can be here. So we might have distinct real eigenvalues. So in this case, you have a node. You still have a node. But we can also have the case where it's split like this. So in that case, you have two complex eigenvalues and they are conjugate of each other. This case, you might have a spiral point. So the theory of the linearization can only tell us about the instability, We don't know whether it is a node or a spiral point. This case a node, this case we will have spiral point. For the critical point 0, 0 of the almost linear system. Let's think about this. If you have a spiral point, for the almost linear case, it will look like this, right? or like this. I don't care whether it is clockwise or counterclockwise. But we are talking about the populations of two species. No way in this world that the population can be negative, and then come back positive, and then negative. We are talking about population, so they are non-negative. This is impossible. So we shouldn't have the spiral point here for 0, 0 of the almost linear system. Linearization theories doesn't have to draw the exact picture here, but at least we know it's unstable. It cannot stay there. It will eventually leave 0, 0 of the almost linear system. In this case, we expect nodal source. Population are non-negative. Special case here. Let's do the second critical point 0, 1. At 0, 1, we compute the Jacobian matrix. Let me do it J1. Jacobian matrix is this one. At 0, 1. So you have 2 minus 0 minus 1 minus 0 minus 1, 2 minus 4 minus 0, 1, 0 minus 1 minus 2. This case is also nice matrix. It is a triangular matrix, so you know that two eigenvalues are 1 and negative 2. Eigenvalues 1, negative 2. So in this case, we have 1 positive, 1 negative eigenvalues. You will have 0, 0 of the linearization. And in our case, 0, 1 of the almost linear. Almost. Systems is a saddle point. So it is unstable. So globally, we know that eventually population will leave this critical point. Right? It will not stay here. It is unstable. To sketch the picture, we want to compute the eigenvectors. In this case, I do know that one eigenvector will be the one correspond to minus 2 will be 0, 1 for sure. Because you think of this as you multiply 0, 1, you will get the second column 0, minus 2, which is minus 2 times 0, 1. By definition, 0, 1 is an eigenvector. So let's compute the other eigenvectors. So for lambda 1 equal to 1. We are trying to find a minus lambda I, a minus 1i, v equal to 0. So we want to minus 1 here. Minus 1, minus 1. 0, 0, minus 1, minus 3. Say we have AB. Let's say we have AB. So this one, V is vectors AB. And this is times AB. 0, 0. then you have minus a minus 3b 0, a equal to minus 3b. So any vectors of the form minus 3b b non-zero, so minus 3 1. Any vector of this form, as long as it is non-zero vectors, it would be an eigenvectors correspond to lambda 1 equal to 1. So choose v1 to be vectors minus 3 1. For the second eigenvalues, lambda equal to negative 2, as I said before, we know immediately one eigenvectors is 0 1. Lambda equal to 1, lambda 2 equal to negative 2. We know that v2 and choose to be 0 1. Explanation. So we know that j1 times v2 equal to lambda 2 times v2. By definition, this lambda 2 eigenvalues, this v2 eigenvectors correspond to lambda 2. So verification here, j1, this matrix v2 0 1, you get the second column 0 negative 2, which is negative 2 0 1. So you see that v2 0 1 is an eigenvectors associated to lambda 2 equal to negative 2. Now we have two eigenvectors here. You can draw, you can sketch picture. v2 0 1 will be the vertical line. So you have minus 2, so let's go inward there. v1 minus 3 1, minus 3 1. So we should have this axis. I sketch a few lines and go outward on the red axis. Go in and then out. Go in and out. This is what happens near the origin of the linearization. And the global picture we will draw at the end. Now let's look at the next critical point. We have 1 0. At 1 0, j2 1 0, you have 2 minus 4 minus 1 0 2 minus 0 minus 1 minus 2 minus 1 0 1. We have two eigenvalues, lambda 1 negative 2, lambda 2 equal to 1. Again you have a saddle point 0 0 of the linear relation and 1 0 of the almost linear system. We will be this one and this one are saddle points, and they are unstable. So to sketch it, I need to compute the eigenvectors to sketch accurately. You know that for -2 here, the eigenvectors will be on 0. Lambda 1, -2, v1, 1, 0. When you multiply 1, 0, you do the same as the previous case. You get the first columns, which is -2 times 1, 0. So by definition, 1, 0 is an eigenvectors correspond to -2. For the second lambda, we need to compute it. If we want to find v2, so that a minus lambda I times v2 equal to 0. This is, I should write j minus lambda I instead of a. So j minus 1 minus 1. This one is -3 minus 1, 0, 0. As soon as we multiply AB for V2, then you have -3A minus B, 0, B minus 3A. So vectors of the form A minus 3A, A times 1 minus 3 will be, as long as A is non-zero, will be an eigenvectors correspond to lambda 2 equal to 1. So I choose V2 to be 1, -3. Now we sketch the pictures of the linearization. So we have lambda 2 equal to -2 V1. V1 on 0, so it's go inward here. And V2 on -3, 1, -3. So it will give us this axis. It's go outward because lambda 2 equal to 1. Positive. So the pictures would be like this. So this is still the pictures 0, 0, near 0, 0 of the linearization. I will draw them all together in the global picture later. We have the final critical point to compute. 2/3, 2/3 Jacobian matrix, the last Jacobian matrix. Two minus 8 times S/3 minus 2/3 minus 2/3 minus 2/3 2 minus S/3 minus 2/3. So you have 6/3 minus 10. So minus 4/3 minus 2/3 minus 2/3 and minus 4/3. This is the Jacobian matrix. Now we compute the eigenvalues. J minus lambda I, determinant of this. Minus lambda minus lambda. So we have 4 over 3 plus lambda square. Right? So originally is minus here, but it's square, so I can get rid of this minus. And minus 2 over 3 square. Yeah, do the same thing. Minus this one times this one. So minus this one square equal to 0. 4 over 3 plus lambda square 2 over 3 square. So 4 over 3 plus lambda equal to plus minus 2 over 3. Yeah. So a square equal to b square. A equal to plus minus b. Here you have lambda equal to minus 4 over 3 plus minus 2 over 3. So you have minus 4 plus 2 over 3, minus 4 minus 2 over 3, so two cases, minus 2 over 3, minus 6 over 3, which is minus 2. So in this case you have lambda 1 minus 2 over 3, lambda 2 minus 2. So they are both negative, so we will have a sink here. 0, 0 of the linearization. And 2 over 3 of the almost linear system. Nodal sink. So this case we know this is asymptotically stable. I need to compute the eigenvectors to sketch the picture. For lambda 1 equal to minus 2 over 3. Minus 2 over 3 minus that. So we have minus 2 over 3, minus 2 over 3, minus 2 over 3, minus 2 over 3. So this case you can eliminate the whole second row, and then this one become 1, 1. You have a plus b 0, b equal to minus a. So vectors a minus a times 1 minus 1. Any vectors of this form, as long as the vector is non-zero, will be an eigenvector correspond to lambda 1 equal to minus 2 over 3. So I choose v1 to be 1 minus 1. Let's do the second eigenvectors. Lambda 2 equal to lambda 2 minus 2. Now here the Jacobian matrix, J minus lambda 2. So you have minus 4 plus over 3 plus 2, so plus 6 over 3, 2 over 3 minus 2 over 3 minus 2 over 3, 2 over 3. This one will be reduced to 1 minus 1, 0, 0. A plus b, a minus b, 0. Any vectors of the form a times 1, 1 will give us eigenvectors as long as those vectors non-zero. Choose v2 to be 1, 1. So now I can sketch the pictures. lambda 1 equal to minus 2 over 3. Eigenvectors v1, 1 minus 1. Lambda 2 equal to minus 2. V2 is 1, 1. 1 minus 1. 1 minus 1. So the first axis is the blue one here. It goes into that. Will be sink in this case. The second one's 1, 1. It's also go inward. Lambda 2 minus 2 less than lambda 1. Minus 2 over 3 less than 0. When you multiply t positive, you have this. E lambda 2t will be much smaller than E lambda t is 10 to plus infinity lambda 1t. This one will decay to 0. Only this term left. When t is 10 to infinity, t 10 to infinity, it is following v1. It's following v1 when t go to infinity. So the pictures would be v1 is 1 minus 1, v1 is a blue one, v2 is a red one. So let's go close to v1. So it's going to go like this. The other side, when t is minus infinity is parallel to this one, but it will be too far away. T is minus infinity. So general pictures near the origin would be like this. For the general picture, you always look at this very close to this critical point 2 over 3, 2 over 3. Here's the 0, 0 of the linearization. Now let's draw on together. X, population Y, origin 1, 2 over 3. So we have 4 critical points: 0, 0, 1, 0, 0, 1, 2 over 3, 2 over 3. We know that for the first case, it is a source, right? A nodal source, because we don't want to do spiraling here. The population will enter the negative side, which doesn't make sense. Here's the pictures when p is around 0 on of the almost linear. Almost linear. Zero, one look like this. Here we have 1, 0. 1, 0 of the almost linear system. They look like this. And the last one is this one. You get the sink. This one's around 2 over 3, 2 over 3. Around 0, 1. So it makes it look like this. Around 1, 0. You make it look like this. Around 2 over 3, 2 over 3. We make it look like this. Yes, I need to erase all of this because it's the two files is when t tend to minus infinity. Now let's connect them. It's going to go like this. Go out here. Go to this point. Yeah, it's going to sync to this point. The direction is sync to this point. We only care about the first quadrant. So expect it go like this. Sync to this point. So here's my sketch. So in this case, you see that if you start everywhere here, the initial condition, eventually the population can be synced to this critical point, 2 over 3, 2 over 3. So the two populations can coexist in this case. The long-term outcomes does not depend on the initial condition. They will coexist.